Shivendra sir, please begin.
Sure, sir. Good morning, all. Today we have Dr. Gaurav Kataria as a guest speaker. Currently, he is working as an assistant professor in Manipal University, Jaipur. He is doctorate in chemical engineering from MIT Jaipur. His research area are soft sensor, modeling simulation, process intensification, process control, and on behalf of Department of Chemical Engineering, PIT, Parul University, I welcome you, sir, and would like to hear from you. Over to you, sir.
Thank you, Shivendra. I think my screen is still again not visible, but let me start. As soon as I get the option, I'll go for it. So, first of all, when we're talking about the process intensification, my first question lies is what is actually a process intensification? Okay, as we all might know that it all starts with the chemistry lab, where we start our experiments with the just at the scale of test tubes and at the scale of beakers. Then we move forward to industries. And let me be very clear: if you are achieving 90, 95%, 99% purity in the lab, that doesn't mean that in the industrial scale also you'll be getting the same efficiency, because as the scale goes higher, the area to volume ratio gets weaker, and because of that your interfacial surface area gets decreases, or the contact area get decreased, and that leads to the decrease in the efficiency as compared to the literature, you can say, your lab experiments. So we start with the lab experiment, we go further to the industries, and then after that also we go for intensification. What is the meaning of intensification? We want to improve that particular system. Whenever we are talking about either vector or exchanger, or you can say column, we all start with the basic process, let's say basic batch process, then we go to continuous to plug flows and all. Our ultimate goal is to first save money. Every industry goes for the one mindset only: I want to increase my profits as much as I can. So whenever I'm going for the intensification, my prime motive is to increase the profits. How will I increase my profits? Either by increasing the efficiency or making my process sustainable, just or making my process more sustainable, or making my process cleaner, or ultimately I want to save the energy. I can also try to decrease the area of my processing unit, so that I can save the space, I can save the inventory. And this goes on, and this ultimately directly leads to the saving my financial expenses. One more thing that I left is safe. Okay, the intensification also, you can say, one motive is to decrease the pollution level. Okay, just remember one thing: how do you create the pollution? How the industries create pollution? It is basically because of the waste. Uh, can anybody confirm that my presentation is visible?
Yes, sir. Yes, please.
Is my
It's
presentation
working, sir.
visible?
It is.
Okay,
Yes,
thanks
sir.
a lot. So, can I start? I think. Can I move forward?
Sure, sir. Sure, sir.
Sure. So after that, we went for, let's say we were talking about the intensification. So ultimately, I want to save money. I want to save environment. I want to save. You can say I want to make it more cleaner. I want to make it more compact. So my first of all, my question is, what is the you can say current state? Because ultimately, when I'm watching this particular picture in 1556 and in 2002, the equipments are quietly the same. There's no much evolution in the particular equipment. It's just the wooden equipments are converted to the, you can say, metal converters. So metal equipment. So am I still in the process intensification mode? Just wait a minute. मैम लेक्चर में हूँ 11 बजे बात करता हूँ. So my answer to this question is yes, I have grown a lot. So you can see over here, if you want to, you can say produce the methyl acetate from the acetic acid and methanol, just a basic esterification reaction. So what was the conventional part? Conventional part was reactor after that 8 to 9 columns, whether it be a distillation column, whether it be azeotropic distillation, whether it be a liquid extraction, solvent extraction. You can name n number of, you can say, equipments just to separate the unreacted reactants, byproducts. So ultimately my goal was to increase the methyl acetate. So the whole process has been intensified to just 3 units. One major unit, which is a reactive distillation column, where my reactants are, you can say, getting reacted and separated in a single column. We'll study this in the further, you can say, in the next presentations. So what are my industrial targets? Ultimately I want to go for the scale. I want to convert these whole big industries to the, you can say, room scale or a small building scale industries. Earlier it used to be bigger was better. Now the funder has changed to smaller is better. Why smaller is better? First of all, less space means less money. Second, most of it, why bigger was better? Because bigger was better because of the growing population, a demand was increasing. So earlier the mentality was that bigger, that means higher production rate. Okay, that's why what they did, they just increased the size of the reactors and columns to overcome the demand and supply situation of the particular market. So now what has been changed? The demand remain the same. Okay, it's in the increasing mode only, but I want to make it more compact. Why? Because I want to decrease the residence time. I can increase the production rate by either increasing the flow rate or by decreasing the residence time. Earlier, I used the approach of higher flow rates. Now I want to go for the lower residence time. So it will compensate the demand with respect to the flow rate. So I want to make it more compact. How can I intensify the processes? Basically there are two methods. Okay, first of all, either I can change the hardware or I can change the method. Like in hardware, I can either change the reactor, like a simple CSG or PFR, to micro reactor, to a mixer reactor, static mixer reactor, to a spinning disk reactor. Similarly, in the case of you can say simple agitators to static mixers. But besides that, you can also change the methods. You can, instead of just going for reaction, I can go for the reactive separation. Instead of just going for a normal column normal column separator, I can use the membrane separator. I can use the membrane distillation. I can use the adsorptive distillation. According to these particular things, my process can be intensified. That can lead to a betterment in every sector, whether it be economic, whether it be in the case of cleaner, whether it will be in the case of sustainable, whether in case of the size, everything will be getting better. How do we do it? This is basically a sustainability of PI, or you can say the basic concept between the for the PI. First of all, PI means process intensification. How do we go for it? What will I do? Let's take the example of simple CSTR that you are already using it. So create this as a base case. Okay, you took a CSTR, you are already using that in an industry. Now what your R&D team is trying to do, I want to intensify it. What I want to do, I want to either reduce the waste. Okay, this section will be going to either I'll be going to reduce the waste, either I'll go to increase the yield, either I'll go for the lower environmental impact, either I'll be going for the higher yield, I'll be restricting the selective, I'll be going for a better selectivity. All these things will be getting intensified either by, you can say, changing the equipment or the method. But base you can say mentality will be, I want to make that particular process better. So I'll be getting few of the other options. Okay, then I'll be assessing it which one is better. Why? In the case of economic evaluation, Okay, which one is giving me higher profits, which one is more safer, which one is more sustainable. So according to that, that new technology will be replacing the base technology. So let's say the CSTR term has been replaced with the PFR vector. Okay, now your R&D team will be start working on the PFR. Then I'll be repeating this particular process loop again and again till I reach the 100% efficiency, which is quite close to impossible. So this loop will run again and again till I go for a, in the case of reactor, I can go for a perfect reactor. What is basically perfect reactor? Perfect reactor is just a base concept. This is a hypothesis which scientists are trying to, you can say, accommodate till 2050, which is basically 100% yield, no byproducts, complete control on the molecule movement, and so on. So I want to make a perfect reactor. That is quite, you can say, is that unimaginable. So now let's talk about the process intensification in separation processes. So whenever I go for the separation process, what things first comes to your mind are the big columns, basic column, distillation column, absorption column, extraction columns. So ultimately columns. So when we are talking about the columns, so let's take an example of a three component mixture. A is lighter, B is intermediate, and C is heavier. So conventionally what will I do? I'll go for either simple direct, where I'll be using a single column where A will be my distillate, and temperature will be in such a way like that A will be in the higher purity in the distillate of the first column. B and C, a mixture of those, you can say binary mixture, will be going to the next column, and B and C will be separated from the distillate and the bottom as a bottom product. And similarly, it can be simply indirect. Instead of going for a lower temperature, I'll be going for a higher temperature so that I can get a pure C at the bottom, and then the above binary mixture of A and B instead of B and C will be going to the next distillation column. I'll be separating A and B from the mixture. The next one is sloppy one. Instead of going for two, you can say distillation, I'll be going for three distillation. Why is it sloppy? Because in the first, you can say column, it is a sloppier one that you're not giving the highly intensified, you can say heat, energy. You're just trying to make it a mixture of, instead of going for a pure A or a pure C, you're going for a mixture of A and B and B and C. Then you're using two other distillation columns and removing A and B, B and C, and mixing this particular bottom and a distillate and making B single one. This was intensified to a prefractionator sequence and Petlier sequence. What is the basic concept in this? You'll be just using the instead of going for the you can say two basic columns, you'll be going for two columns. But in the case of prefractionation, the first will be prefractionator and the second will be the fractionator. In prefractionator, you'll be just giving them the heat to go for a sloppier separation where A, B will be the distillate, B, C will be the bottoms. And this will be going to a bigger column, which will be a fractionator column, where you'll be getting A in the distillate, C from the bottoms, and B as an intermediate product. What is the difference between a prefractionator and Petlier? In just this case, the sloppier one doesn't have do have a you can say condenser and a reboiler, but in the Petlier there's no reboiler condenser. Instead, you're just going for, to give a heat, you're just going for the reflux, which is actually carrying some heat, which will be used to run this particular column. After that, the more intensification was done, there was side stripper and side rectifier. In this particular case, will in according to the volatility, according to the availability of B at particular point. So you can imagine that B can be higher at this point, at this point, at this point. So totally depending upon the, you can say, purity of B, the volatility of B, you'll be just taking a stream of a liquid out of the system. You'll be going for just a small unit over there. You'll be just, you can say, you can either flash it or you can use a simple heater to remove B from a side product, and A and B, which will be higher A and lower B content, will be recycled back, you can say, as a side reflux to the column. And this can also be gone through side rectifier also. Okay, so it will be totally depending upon, is B closer to A or B is closer to C. That means is the you can say boiling point of B is closer to A, that is of a distillate, or boiling point of B is closer to the C. If say let's say it is in the middle, then this stripper or rectifier will be in the middle. So that will be the case. So this position will be totally depending upon the boiling point of B. And the most intensified and the most important, you can say, process of this is a divided wall column. So what actually happens, let's say a reflux is coming from the first tray, second tray, okay, it will be coming down as a liquid which will be containing higher content of A and B. Okay, as it moves downwards, the A will be getting vaporized and it will be getting back to the condenser. What will be remaining? A very high content of B and very low content of A. Okay, this will be, if in the case of conventional one, will be getting mixed with the feed, which is not pure at all, and it will be contaminating the whole liquid that is coming from the upward section. What I want to do, since the liquid coming from the above upward trays is quite, you can say, pure in B, I'll be separating it in this section only. But how will I do it? Because my feed needs heat. Okay, from where is it? Will it be taking the you can say vapor liquid equilibrium by incoming the vapors from the lower section and from incoming liquid from the upper section. So what will I do? I'll apply a splitter, liquid splitter over here and vapor splitter over here. What will it do? It will split the liquid in certain ratio so that a small amount of, you can say, liquid is going to the feed section and small amount of liquid is getting collected as a product B. So you can see over here, uh, this is a vapor splitter and this is a liquid splitter. The splitting will be happening that few of the liquid, certain amount of liquid will be going to the feed section, that is pre-fractionator section, and the other one is the main column where I'll be getting a side product. So my main motive is to not to make a contact of higher B with the mixture of feed, because ultimately A, B, C are quite impure as compared to the liquid stream coming out of from the upper section. And similarly, the vapor stream that is coming out from the bottoms is containing very high, you can say, B content, and if it gets, you can say, mixed with the feed content, it will be getting contaminated. So I'll be going for a partial amount of the vapors will be sent to the free fractionator and the partial will be sent to the main column where B will be getting out of the system. This is a wall. So basically I'm just applying a wall in between the trees. Just a small video for this for the better visualization. So this distillation mainly contains normal reboiler and condenser. Okay, just a wall in mid of the trays. These are the basic reboiler and condenser. These particularly works at the 80% of the total energy efficiency. There is a liquid splitter, there is a vapor splitter. You'll be giving them a liquid split and the vapor split in the certain amount of ratio, that how much will be going to the one section and how much will be going to the second section. This is pre-fractionator. This is the main fractioner column. Okay, there's some vapors coming in the pre-fractionator column. There's some you can say in going the main fractionation column. These are the particularly this yellow you can say nozzle will decide how much to send over here and how much to send over there. So over there we just studied that the wall is in the middle of the section, but that is not a necessary you can say technique. Totally depending upon the B, totally depending upon the volatility or the boiling point of B, this wall can be also taken downwards or upwards, just like a side stripper and a side rectifier. Next is the DWC divided wall column is not restricted for the 3 products only. It can also go for 4 products, 5 products. But the more will be the products, the difficult will be the you can say complex. More complex will be the column. So in the case of let's say 4 products, either by using one wall, I can go for AB over here, CD over here, and A will be going to the distillate, B will be getting as an intermediate. Similarly, D will be getting as a bottom product, C will be getting from the intermediate. In this case, the all remain the same, but there is a blockage wall. Okay, what it does that it doesn't let the B go downward from this tray to this tray. This will be totally blocking it, and the blockage liquid will be in the case of B only, and the upper section will be showing you C. This can be useful when the boiling point between the B and C is quite close. It doesn't have that much, you can say, difference. In the case of just using a single